Okay, so in this video we are going to learn about molecular polarity. Just want to specify here that in previous videos we have looked at polarity of bonds, but this is the polarity of the molecule as a whole. So molecule would have many bonds there, might have many bonds, and all those bonds may be polar, maybe non-polar, but when we talk about molecular polarity, we are talking about the molecule as a whole. So before we go there, just a little bit of recap as to what we have done in previous videos. We looked at the octet rule, and I just want to put in a word of caution here that octet rule is not universal. Octet rule is not universal. What it means is that when atoms are bonding, they may not always end up with an octet in their outermost shell. Yeah, in many cases, the atoms would not have a full octet. We will call it incomplete octet, and they would still form bond. And just as we have incomplete octet, we have expanded octet as well. So when some atoms, particularly those from period 3, like we got sulfur and chlorine and phosphorus, these are in the third group, and when they make bond many times, they have more than 8 electrons in their valence shell, and it's a situation which we call expanded octet. Okay, but we are not going to study these things because they are not they are outside the scope of this video. That was just a word of caution that you need to be aware of. But as far as this playlist is concerned, this series is concerned, we will limit ourselves to octet rule only. All right, let's go to molecular polarity. So when we want to find out whether the molecule itself is polar or not, what we mean by that is suppose this is a molecule, and we want to check whether this molecule has a delta minus delta plus kind of thing or not, whether it is polarized or not. And it would depend on many factors. In fact, it would depend on two factors. One is the bond polarity, the polarity of the bond, polarity of the bonds making the molecule, and the other one is the shape of the molecule. Yeah, therefore, determining the molecular polarity would depend on, would require you to have watched the previous videos really carefully. So we start with examples. So, okay, before we take an example, let's talk about bond polarity. So we talked about the molecule of, let's say, water molecule here. Let's talk about water molecule. And we know that the shape is like this. Yeah, this is a hatch here, this is a hatch here you have, and this bond, each of these bonds are polar. So this bond is, and that bond is polar. You have delta plus here, you got delta minus here, you got delta minus here, you got delta plus here. So these are the polarities of the bond. Now, polarity is a vector quantity, and what I mean by that is, let me do it again. Polarity is a vector quantity. What I mean by that is polarity has a direction, and normally polarity is all right directional. Yep, vector quantities are quantities which have direction as well as the magnitude, and their addition depends on the direction as to in what how the two vector quantities being added are oriented. So simple example is that when you are adding, when you got 5 kilogram of sugar and you add 2 kilogram of sugar, you will always get 7 kilogram. That is a scalar addition. But you got a force of 10 Newton and you got a force of 5 Newton, you add them, then the output result will depend on the direction of these two forces. So if both the forces, this is 10 Newton in this direction, the 5 Newton is also in this direction, you add them, you will get 15 Newton. But you got 10 Newton in this direction and 5 Newton in this direction, you add them, you get only 5 Newton because they cancel out. So polarity is a directionalist vector quantity, and normally it is measured in terms of what we call dipole moment. But we are not going to rely on that. We'll keep it simple and we will say that polarity is directional and it has a direction. So and it is shown like this. So this bond between hydrogen and oxygen is polar. We normally show it like this. So that's it's a sort of a force kind of thing you can see here, and you got the other one as well on this side. Yeah? Basically this arrow represents the direction of shifting of the electron cloud. So oxygen is more electronegative, so the shared electrons will shift towards oxygen, and that is the direction of a dipole moment. We won't call it dipole moment, as I told you. We'll keep it simple and we will say that this is the polarity. That indicates the polarity. Now polarity is like a force, as I have told already, and the polarity of the molecule will depend on how these individual polarities add up. Yeah, so let's take a simple example of carbon dioxide. So carbon dioxide is the electron dot. You'll need to draw the electron dot diagram. So we got that as our electron dot diagram, and then we see that it is like this. VS-EPR theory says that multiple bonds are to be taken as single bond. So these are two single bonds, or known as, or you can call them single electron pairs, this and this, and they repel each other, so they end up being as far away from each other as possible, and we have the shape of this molecule as linear. So it's a linear shape. I mean draw this. I don't need to draw it here. And each of these bonds are polar because oxygen is more polar than oxygen is more electronegative than carbon. So we have that kind of thing here and that kind of thing here. Yeah. So carbon dioxide has polar bonds. But when it comes to polarity of the molecule as a whole, we need to add these two forces, these two polarities, and as I told you, they are vector quantities, and we add them just like we are adding, just like we add forces. So these two bonds, these two forces would be of equal magnitude. They will be these polarities will be equally powerful. So when you add them, because they are in opposite direction, they cancel out, and the molecule itself is non-polar. I hope it makes sense. Let's look at one more example of methane. You got CH4. We know the shape here. We know that the shape is tetrahedral, or the 4 hydrogen atoms are pointed towards 4 corners of a tetrahedron. So that's what you have here. That's a wedge kind of stick here, and that's a dotted stick, which basically means that the bond is behind the page, and this is coming out of the page towards us. Now it's a tetrahedral, it's a tetrahedron, and all these bonds have equal polarities. Now here, I want to make it clear that the difference between difference in electronegativity between carbon and hydrogen is very small. So effectively we take carbon hydrogen bond as non-polar. But for the sake of this discussion, we say that there's a little bit of polarity there, bond polarity there, because carbon is little bit slightly more polar than hydrogen, so slightly more electronegative than hydrogen. So you would have that kind of thing there, it would have that kind of thing here, that kind of thing here, and that kind of thing here. And it's a regular tetrahedron. So all these four polarities, they are of equal strength, they are equal polarity there, equal strength, so they all add up to make the methane molecule non-polar because they all cancel out. So CH4 is non-polar. Let's look at another example, and then I will put a twist in methane molecule. So let's take the case of carbon tetrachloride, which is a form of methane in which all the 4 hydrogen atoms have been replaced with 4 carbons. So same shape is there. Shape is very important because if they are shaped in, if the molecular shape is regular, then the polarities can cancel out, otherwise they will not cancel out. Sorry, so Cl. Now here it's very clear, chlorine is much more polar, much more electronegative than carbon, so the polarity can be shown like this. So bond polarity is like this. So in CCl4, individual bonds are polar, but because this is a regular tetrahedron and all these polarities, because all of these are bond between carbon and chlorine, so all of them are equally powerful, equal polarities there, so they all cancel out, and what we get is a non-polar molecule. So CCl4 is non-polar. Okay, now let's look at a methane in which one atom has been replaced with chlorine. So we saw that methane molecule is non-polar, but in this methane I have replaced one hydrogen atom with chlorine. So the shape will be still tetrahedron. You got, this is Cl, that's H, that's H, and this is H. Now I want you to pause the video here for a moment and tell me whether the molecule will be polar or not. Now you can see here that they are, I can take all of them as polar bonds, hydrogen carbon bonds as well. There's slight difference there. So you have that kind of bond polarity here, and then you have that kind of polarity here. Now just need to remember that difference between electronegativity of chlorine and carbon is much greater. So this bond, CCl bond, is much polar. In comparison, all three bonds are very less polar, so they do not cancel out, and CH3Cl is a polar molecule. And let's look at one more example. So we'll look at the water molecule here. You got water here, and this is hydrogen, this is hydrogen. The bond polarity can be shown like this, and obviously we can see that the bonds are not polar, bonds are polar, and they do not cancel out because geometry is not like when they would cancel. Yeah, they would cancel if they were in opposite direction, but here they would not cancel. So H2O is a polar molecule. And we'll just look at one more example, and that example is of that of ammonia. So ammonia, we already know that the shape is like this. So we can draw a wedge kind of thing here. Not really beautiful. So that's the wedge, that and that. So this is H, this is H, this is H. Nitrogen is much more polar. So you get this polarity, you get that polarity, and you get that polarity. And we can see that these polarities would not cancel, although all these three bonds, they have same amount of polarity, same dipole moment, so to say. They will be equally strong in a way. So but they are not oriented in a manner where they could cancel. So NH3 is a polar molecule. So just to sum up, to find the molecular polarity, what we need to find two things. Find the polarity of individual bonds, polarity of individual bonds, and then you need to know the shape of the molecule. You need these two things, and then you can make a decision about whether the molecule is polar or not.